Continuing to talk about pH and pOH, these are two examples of pH meters. A research grade pH meter is used in a laboratory and can have resolutions of extremely accurate and precise evaluations of pH to units of 0.001. And remember, this is a logarithmic scale, so we're talking about very accurate with plus or minus 0.002 pH units. But these cost a lot of money. Now other units are more portable and they have less accuracy, but they're far cheaper. There's actually paper that is used. Here's a couple of examples of indicators that are used. On the left here you have an indicator that assumes a different color depending on the pH. And so it can be added to a solution, and then the color can be looked at and can tell you with some degree of accuracy. Now obviously when a person looks at something, there's a certain degree of subjectivity as far as how dark a yellow or orange or blue it is, and various people such as myself could be colorblind, so they can have difficulties telling the difference. On the left, or excuse me, on the right here we have what's called pH paper that has different indicators mixed onto the paper, and then they change colors based on the pH. It's commonly used to test, for example, urine, to see what the pH of urine is. And here are some ideas, or this introduces the ideas of strong versus weak acids and bases. And the table here shows 5 or 6 strong acids and 6 strong bases. Well, a strong acid or a strong base is determined by what the acid-base ionization constant is. This is the equilibrium constant for an acid or a base. You'll remember we looked at this briefly in previous slides, and it's the product of the concentration of the products, which are generally hydronium ion times some other ion, divided by the concentration of the unionized acid. And you'll note that in a situation of the strong, that most of the protons are donated and very few are left with the native compound. So you have the equation, which looks like this, where you have an acid plus water gives the hydronium ion plus the acid anion, and the Ka for that is going to be the product of the two concentrations of the two products divided by the unionized or the non-reacted concentration of acid. Now in situations of strong acids, the products are favored, so the numerator is going to be quite large, the denominator quite small. And this is an equation that you'll want to keep your hands on. Calculate the percentage of ionization of a 0.125 molar solution of nitrous acid, which is a weak acid, if it produces a pH of 2.09. Well, let's take a look at that. And this is akin to some of the problems you did last week in your equilibrium problems, except it's specific for acids and bases. First of all, we know that what we have here is a nitrous acid. And it's going to be added to water to form the hydronium ion plus the nitrous ion, anion. And so the equilibrium constant here is going to look like this. Divided by the concentration of HNO3. And this is going to be Ka. Now what we've done here is we've told you two things. We've told you this number, so that the concentration of HNO2 is going to equal 0.125, and we've told you the hydronium ion concentration as well by telling you what the pH is. So if the pH is 2.09, which is going to equal minus log to the base 10 of the hydronium ion concentration, if we solve for that, the hydrogen ion concentration comes out to be 8.1 times 10 to the minus 3. So we know that. Now at this point we can actually calculate. We don't really need to know this, although we do know this because for every one of these you have to get one of these as well. And so now we can calculate this percentage. And the percentage ionization is going to be 125 minus 8.1 times 10 to the minus 3 divided by 0.125 times 100. Actually, this number is going to tell you how much is not. It's 93.5% unionized. And so the subtraction of that, or 6.5%, would be the percentage ionized. In other words, what we have here, what we should do is take this and subtract this and use the negative number for that. But it's better to do it this way and just say that this is how much of it does not ionize. And then the subtracting that from 100 gives you the percent of ionization. Let's do another one. It says calculate the percent ionization of a 1 molar acetic acid whose pH is 2.89. Again, it's the same idea. We do the same. I'm not going to write all this again, but if the pH is equal to 2.89, then the hydrogen ion concentration is going to be 1.29 times 10 to the minus 3. So that's the hydrogen ion concentration, or the hydronium ion concentration. And we know that the total is 0.1, so if we subtract 1. This is going to be the percentage that's not ionized, right here. And then we can subtract that from 100, and that will tell us the percentage that is ionized. So this is 98.7% non-ionized, which will be 1.3% ionized. Now let's look at the situation in terms of the bases. This diagram shows the relative strengths of the conjugate acid-base pairs as indicated by their ionization constants in aqueous solutions. Strong acids are associated with weak bases. So the strong acid H3O plus is associated with a weak base H2O. The strong acid HClO2 is associated with the weak base ClO2 minus. Going to the other end on the right side, a weak acid H2O is associated with a strong base, the hydroxide ion. A weak acid HPO4 2 minus is associated with a strong base PO4 3 minus. A weak acid H4 plus or ammonium plus is associated with a stronger base NH3 plus. You notice that the relationship is that the stronger the base is, the weaker the relative conjugate acid is, and conversely the weaker the acid is, the stronger the conjugate base is. And the converse is true as well. So the base ionization constant, Kb, is the equilibrium constant for the base, and that is this formula, and it looks very much the same, except now we're talking about the OH concentration instead of the hydronium ion concentration. And this is another formula you need to keep in mind. Now the interesting thing is that as you increase the strength of an acid, you decrease the strength of the conjugate base, and conversely, as you increase the strength of the base, you decrease the strength of the conjugate acid. And that's exactly what this table tells you. And so what this ends up being is if you take the equilibrium constant for an acid times the equilibrium constant for the conjugate base, you get the equilibrium constant for water. So the larger the Ka, the smaller the Kb has to be. Conversely, the larger the Kb, the smaller the Ka. And that's why these two relationships are inverse this way. Use the Kb for the nitrite ion, 2.22 times 10 to the minus 11, to calculate the Ka for its conjugate acid. We just said that Ka times Kb is equal to Kw. We know that Kb is 2.22 times 10 to the minus 11, and we know that Kw is 1 times 10 to the minus 14. So that means that Ka times this 2.22 has to equal 1 times 10 to the minus 14. So Ka has to equal 4.5 times 10 to the minus 4. And if you take 4.5 times 10 to the minus 4 times 2.22 times 10 to the minus 11, you're going to get 1 times 10 to the minus 14. We can determine, looking at the second problem, we're going to have to come back and look at this one later because it's not written out properly. The pH paper indicates that a 0.1 molar solution of HCl, the beaker on the left, has a pH of 1. The acid is fully ionized, therefore it's a strong acid, and the hydrogen ion concentration is 1 times 10 is 0.1 molar. A 0.1 molar solution of acetic acid, the beaker on the right, has a pH of approximately 3. The hydrogen ion concentration is 0.001 because the weak acid, acetic acid, is only partially ionized. In this solution, the hydrogen ion concentration is less than the concentration for the unreacted acetic acid. The pH paper indicates that a 0.1 molar solution of ammonia on the left is weakly basic. The solution has a pOH of 3, which corresponds to a OH or hydroxide ion concentration of 0.01, because it's the weak base ammonia only partially reacts with water. A 0.1 molar solution of sodium hydroxide on the right has a pOH of 1 because sodium hydroxide is a strong base.